Hi everyone, we'll start soon. Don't go away. Just want to make sure that you know I'm here. Hi everyone. It is 3:30 here in California, so let's get started. Welcome to free Mathcounts training. My name is Kai Zhu. I'm a parent here in Silicon Valley, California. I was the head coach of Mathcounts for the last 2 seasons here at a local public charter school, Bolis Charter, in Los Altos. This year, I will help one of my former students to continue to coach the Bolis Mathcount team. However, I will let my student to take over the head coach job. That student did very well last year in Mathcounts. He made the national team from California, which was very impressive because California, as you know, is the most popular state, and the competition here is really, really heavy. And because each state can only send 4 students, its top 4 students, to the national competition. So that was a remarkable achievement. Anyway, I want to talk about our training program for this school year. This is a 30-week long training program for Mathcounts because you know Mathcounts will generally start competition in January or February, the latest, depending on where you are. So this 30-week training program is not aligned with the current season, meaning that if you plan to compete this year, probably you won't be able to finish the whole training program. Then the competition will start. So if you start your Mathcounts start your training fairly late, say you're 8th grade already, but never train or compete in Mathcounts before, you still will get some benefit from this training, but you cannot finish the whole program. If you are, say, a younger student in your 6th grade or even just even younger, then what you can do probably is that if you want to compete this year, that's fine. But possibly after finishing this whole year program, you can compete again next year, and I'm sure you will become a stronger math student. So it's not perfectly aligned with the season, nor did I want to, because 30 weeks is a reasonably long period, and we can have enough time to present just all kinds of topics to you that will be actually tested in Mathcounts. So our training program borrow materials heavily from those jointly developed by Mathcounts, the official Mathcounts organization, and Art of Problem Solving. So if you go to our website, which is www.freeasianmath.org, there's a sub-page for this program, which is free Mathcounts training. We acknowledge the great materials developed by those people at Mathcounts and ALPS. So we are really, really grateful for their hard work. We want to thank them here. So there's a FAQ, frequently asked questions and answers page at our website, which outline how we are gonna carry out the training. So there are detailed step-by-step instructions for you guys what you need to do each week. So what happened is that the Mathcounts and AOPS teams, they jointly developed about 100 so-called mini unit. Each of the mini unit focus on one mathematical topic. Could be geometry, algebra, number theory, just one topic. Then they chose some past Mathcounts competition problems, very representative. So they made a short video. Typically, it's about 10 minutes, plus or minus. A mini video discuss one or up to three, sometimes it's two, sometimes it's three, sometimes it's more complicated problem, just one single problem in that video. Then they provide some worksheets. Actually, before you watch the video, there are some so-called quote-unquote warm-up problems. Those are easier problems, but just you should do that to get warm up. Then you take a look at the video problems, which is harder. Depending on, I'm not sure exactly how they decide to choose those problems, but I believe those problems from Mathcounts state or sometimes could be chapter. Those problems are kind of medium difficulty, not too easy, but not excessively difficult. So kind of right. So you need to work on that or those video problems all by yourself before you watch the video. If you can work it out, great. If you cannot, no worry, because they produce the video to discuss those problems. So then you watch the videos and learn from the video. If you saw that you actually work it out, maybe you want to compare your own solutions to the solutions in the video to see whether their methods or their approaches are better, or maybe yours are better. Just never underestimate yourself, right? So then after watching the video, you should do the follow-up problem. That's the key. So each worksheet gives you several follow-up problems that are closely related to the topic of that mini. So that's why we are here today. And actually, each Sunday when we are in session, we spend 1 hour to discuss some of the more challenging problems in those follow-up problems. So that's just per unit. But we only have 30 weeks, and there are 99 actually, because they have 100, but last one did not really give you any exercise. So let's face it, we have 99 mini units. So every week, we will assign you 3 to 4 mini units. We have carefully just regroup those mini units so that each week, the 3 to 4 units are closely related. Sometimes they're just exactly on the same topic. All the video problems are distinct, meaning that they never recycle the problem in the videos. However, in the follow-up problems, you will see later that they do recycle some of the problem, which is a good thing for you guys, right? Because you actually have less work to do, because let's just say in 1 week you have 3 or 4 related to the minis. Some of the follow-up problems are the same across those multiple units, meaning that you actually have a slightly easier workload for that week. So anyway, that's how we are going to carry out our training, I believe at the end of this training, after going through 30 weeks, you will become a much stronger math count student or math student in general. So we do need to provide a little bit of warning here, because in general, this training is about at a medium level. It's not a beginner's just level, but not too difficult or challenging for those very experienced math count students. So what that means that in order to be able to do the problem in training, you should generally have studied pre-algebra. Because if you never study pre-algebra, then almost everything we discuss will sound kind of just unheard of to you. That's not fair to you, because you thought that you're a bad student, but in fact, you have not studied the prerequisite just the materials. So this is one of the just a dilemma faced by math count student, right? Because you can compete in math count when you are in grade 6, 7, or 8. So that's a quite wide range across 3 grades. So that if you are younger, say you're only in grade 6, it would be unfair for you to compete against the grade 8 students. But it is what it is. So this may put a lot of pressure on younger students to go into a kind of arm race, right? So if I really want to compete in grade 6, I may have to just study pre-algebra in grade 5 and finish all that kind of just a 3-year curriculum in 1 year, just for me to be able to say participate in this particular training. But on the other hand, we really don't want to put undue pressures on young students like you guys, right? So you don't have to completely finish a pre-algebra program. You can learn something along the way, on the fly. So it is possible that for the 30 weeks, for some weeks, you are familiar with that particular topic, you feel comfortable to work on the problem. But for another week, say, for coordinated geometry, you have not studied that topic at all, then you may run into a little bit just trouble. But it will also be a great opportunity for you to learn some just new things along the way. You have 1 week. So if you really work hard, I don't see why you cannot at least have a reasonable understanding of the topic before we discuss those challenging or more challenging problems on Sunday. So each student is different, and we don't assume anything. And if you are, say, in only grade 4, or if you are in grade 9, but you never did any competition math work, this might be right for you as well, because let's face it, competition math is more difficult, more challenging than your typical Common Core school math. Math is truly important, and math is also fun. The hope here is that we provide this program just help students who may not be able to access certain, extracurricular resources to get more just from some already available resources on the internet. Anyway, that's my pitch for you guys. So we will start slow, meaning that for the first couple of weeks, we deliberately chose the relatively easier mini units, but the difficulty level will gradually pick up. By the way, if you want to compete in AMC, be the AMC 8, AMC 10, this would be a great cross-training opportunity as well. Typically, because Mathcounts has 4 different levels: school, chapter, state, and national. It's not easy to directly compare Mathcounts with AMC, but I generally believe AMC 8 is about at Mathcounts chapter level, And AMC10 certainly is more difficult in terms of the contents, the coverage is more difficult than Mathcounts. So perhaps Mathcounts state is something like AMC9, meaning that somewhere between AMC8 and AMC10, but of course we know there's no such a thing called AMC9. So Mathcounts could be a great cross-training program for your AMC preparation. So let's get started with this week's mini problems. This week we gave you 4 Mathcounts minis. One of them is about number theory, but the others are more about word problems. So let's spend a couple of minutes to talk about word problems. In general, in elementary school, you are supposed to solve word problems without algebra. That should be a great opportunity for you to develop your mathematical skills, because algebra certainly is a powerful tool, and it's quicker and more convenient to use algebra to solve word problems. However, with such an advanced tool, you may overlook some very basic skills that you could or should develop before you study algebra. And that's particularly true with word problems. But unfortunately, in this country, people just kind of neglect the need to solve word problem without algebra, because once you have that powerful tool, word problems can become easy. This is very unfortunate because it's a missed opportunity, but it is what it is. So let's talk about solving word problem by algebra. The best thing about algebra is that it will hide a lot of just details to the process of solving the equation. So the most important thing for using algebra to solve the word problem is to read the problem carefully to understand what kind of information the problem presents to you. So you do need to read the entire problem carefully. All right. So ask yourself such questions: what are the givens? Meaning that what are the already know data or already available information? And what are the unknowns? Generally, those are one or more than one quantity that you are expected to solve within the word problem. So you can also consider that problem like this from a computer program perspective, because I know some of you have already started computer programming, maybe using the language like Java or Python to do some coding. So think about this: already available information just like an input, and you need to generate some output out of this process. But the most important thing is for you to identify certain relationships, okay, among all the givens and among all the unknowns and among all of them. Essentially, you have to establish from the knowns to the unknowns certain relationships. And the words in the word problem, they are in English, right? So they generally describe or suggest relationships. That's how we naturally use the language. We describe or suggest certain relationships. On the other hand, the relationships will give you what? Equations. Because each relationship, when you view it from English perspective, it's just verbal description. But you should be able to translate that English description into a mathematical relationship, meaning that you will get some equations. So this is actually why algebra is so powerful. Essentially, without the algebra, you will have some unknowns in the relationship. To figure them out, it's not easy to do some forward reasoning. You have to do something like a backward from some knowns to reason back. But once you have algebra, you can just translate that English relationship into a mathematical relationship. So everything will be in the forward direction. If a sentence gives you, say, person A is 2 years older than person B, what does that mean? If you use A to represent person A's age and B represent person B's age, you'll simply write A equals to B plus 2, right? Because that's what the English tells you. It's very straightforward. You essentially just need to translate that statement from English into a mathematical language. And that's how we use algebra, use symbols to represent some unknowns to do that. So that's the general setup for you how to use algebra to solve word problems. So let's take a look at our first problem today. This is problem number 9 from Mini 19. And this is, I believe, is quite similar to the problem in the video in Mini 19 that you already solved. So essentially, in this problem, we look at 4 variables. They represent yellow, blue, green, and red. And we would have 4 equations like what we have here, right? So in the video, they actually create one more variable. You can use a variable, in this case, it's capital A represent all the colors together. But that will give you one extra equation because you have 4 colors. If you introduce one more variable, that will be clearly, this naturally will give you that new, what is the other color? Yellow, right? Yes. So plus y, you add one more variable here, but you also get one more equation. So in algebra, typically, when you have a couple of unknowns, you need the same number of equations to solve those unknowns. And those equations cannot be dependent on each other. They have to be totally independent of each other. So the number of equations you have to match the number of the variables you have, unknowns you have. And if they're not dependent on each other, then you will be able to solve the variables. So in this case, if you do not think that way, let's just say we do not want this variable A, we just want to work with those 4 variables, then in general, you need 4 equations. And that's exactly what we have here, okay? So the question here is that if you do not follow the approach in the video, just want to work with those 4 equations, how can you quickly solve those variables? Well, in math, especially for challenging problems, the most important thing for you is to read the problem carefully and observe the information available to you carefully. Sometimes a shortcut does exist, or at least there are some clever ideas just specific to the situation that is readily available. So in this case, what is something really interesting here? So you can see that we have 4 colors and we have 4 equations, but how do those equations look like? Well, you recognize that in each equation, exactly 3 colors appear, right? Meaning that there's one color is missing, but how that is set up. In fact, each of the four equations has exactly one color missing, and in a rotational fashion, meaning that all the four colors misses exactly one time in one of the equations, right? So for example, in the first one, you don't have red. In the second one, you don't have yellow, you don't have white. And in the third one, you don't have blue. And finally, in the last one, you don't have green. This is a kind of symmetrical, rotationally or cyclically symmetrical. That's a very interesting fact. But how can you take advantage of this fact? Well, because of this kind of cyclical symmetry, they kind of, each color is on an equal footing with the other three, right? Because that particular color missed exactly one time from one of the four equations. That suggests that if you combine all those equations together, everybody will be happy because they will all be in the same situation. Everyone missed once, so if you add all the four equations up, then they all miss one wrong, right? What that means is that if you add all the equations together, on the left-hand side, each color will appear exactly 3 times because it missed once. Agree? So that means that if you add it up on the left-hand side, it's really 3 times for each color. So you can actually get something like this on the left-hand side. Because 4 equations, each color is missing once, so appear 3 times. You add them up, everybody is in the same situation. So you can certainly factor out that 3, and you get some number on the right-hand side. In this case, 45 times 3, that's 135 plus 60, that's 195. All right. By the way, everybody should be really good at numbers, meaning that when you do things like this, add 45, 45, 45, 60, you will immediately recognize that you need to multiply 45 by 3, and you should have some good mental math capability. You will know right away that's 135. You don't want to spend time on scratch paper. Oh, what is 45 times 3? Oh, 15, 1, 12, that's 135. Yeah, you can do that, but you won't be able to perform well in a math competition because Mathcounts, just like AMC, it's a heavily time constrained competition. You are supposed to be super fast to get a good result. If you spend time on things like this, you won't go very far. So this is just like, play basketball. You cannot compete at a high level without mastering all the basic skills: shooting, dribbling, passing, defense. All those basic skills you need to practice a lot during just your practice time, not try it during the real game. Okay, so if you do things like this during the competition, I'm sorry, my friend, you really cannot go very far. So with this, now we can see that we can easily get the sum of all the 4 colors. That will be 19 divided by 3, that's 18, so 6, 5. So you get this result. And from here, you can clearly see you can get each color just by subtracting each equation from this one, because now this is sum of all the 4 colors. You subtract 3 of them, you get 1 color. So that's how you solve this problem. We will just not finish it because this is so trivial. But the idea here for this problem is that you really need to be very observant and take advantage of this information available for you. Of course, this problem represents a special case where you do have such a nice opportunity, and in general, you cannot assume that. But whenever the opportunity presents itself, you should take advantage of it. All right? So let's move on to the next problem. Okay, this is problem number 7 from mini number 55. So this is a simple problem, and very similar to the one in the video. However, we will go through it just as an example to demonstrate what we mean by translating from English into math, from English statement into a math problem, right? So here, the pond has three kinds of dogs: a pit bull, a chihuahua, and a moose. So of course, we'd like to use the same letter to represent each variable. So we represent the number of pit bulls as P, and chihuahua as C, and M as the moose, so on. So we have three variables. So all but 23 of the dogs are pit bulls. Okay, so that means that you have a relationship right here. What does this English just statement tells you? Or just other than 23, but 23 of the dogs are pit bulls. Okay, so if you have just all of them, that would be P plus C plus M equals to all, right? This is how the video used all but 23. Okay, that means that you subtract 23 from the all. That means that if you subtract 23, then on the left hand side you also want to subtract 23. And what is that number? That number actually represents the pit bulls, right? So what this means is that this is actually the P. Agree? You subtract 23 from all the dogs, that would be pit bulls. But look, this is essentially what you have is something like this, equals to P. So you can see that P can be eliminated from both ends. So that's the actual equation you'll get from this statement. And logically, it's exactly what the English language actually tells you. It tells you in an indirect way. It says all but the 23 of the dogs are pit bulls. That means that 23 represent all the non-pit bull dogs. And what are they? They're just C and M. That's exactly what kind of equations you should write down. What we just wrote here was just an analysis for you to see how this is actually the case. We do a direct translation from English to math at this step, because all minus 23, that's pit bull, but it indirectly tells you this is the real interesting equation you want to write down. All but the 23. Those means the non-pit bull dogs, the total is 23, and that's chihuahua plus moose. So we got our first equation down from this first statement. That's the first statement. And similarly, you have two more statements, but once you figure out the first one, the rest is very similar without any doubt. All but 17 are chihuahua. And that means that the P and the M together would be 17. And finally, you have the last statement, all but 28 are moose. That means the pit bull plus chihuahua would be 28. So that's the system of equations you will be able to write down after examining all the statements. So essentially, you get a system of three equations where each variable, P and Cm, appears exactly twice in two of the equations, but missing from the other equation. And this is almost identical to the problem we just solved in that color problem, right? It's very similar concept. You can go through the same procedure. You add the left arm, then divide it by 2, get a total of the 3 kinds of dogs counting. But we will not do that. So this is how you should understand what you need to do with word problem. Every statement in English reveals a certain relationship. Sometimes it's as simple as say A is 2 years older than B, so you write A equals to B plus 2. But sometimes it could be a little bit more convoluted, more indirect, like in this one, all but 23 are peoples, but if you start right, you set all the 3 dot count as P and C and M, you will recognize that this is indirectly telling you C plus M is just 23. All right? It didn't tell you directly, but it's exactly the same relationship. It just takes a little bit extra effort. But you may ask, well, I'm not that good at the math. I do not immediately recognize this is telling me that just a C plus M equals 23. Well, that's where you need to practice. After doing enough problems, you will be able to see this in a much quicker way. So that's why actually math makes you a smarter person. All right? Write that down and convince yourself that's the case because it's a fact. It's not a theory, it's a fact. Math makes people smarter. Okay, so that's the second problem of the day. Okay, let's move on to problem number 3. This is problem number 7 of mini 82. Okay, let's clean our whiteboard a little bit. So what does this problem say? Well, you have a rectangle. Okay, we have some geometry problem, but that's okay. A rectangle has area 10A square inches, and the perimeter is 42. Okay, so we actually, this is a quite just succinct but information-rich statement. It gave you 2 numbers, okay, which actually, because the perimeter and the area, they're kind of separated. So what this means is that you will be able to get 2 equations out of this, but we'll see what they are. Okay, if the length and the width are both increased by 1 inch, then what is the area of the resulting rectangle? Okay, so before we go back to the first statement, let's examine the second sentence. What does that sentence tell you? It says that if the length and the width are both 1 inch longer, this is the hypothesis, right? It's if. It does provide some information, but it did not give you any additional information. It asks you a question directly. What is the area of the resulting rectangle? So, in this second sentence, do you really have a relationship? Actually, don't. Because it does not tell you any additional information. It just says if the length and the width are both increased by 1 inch, that's a hypothesis. Then it asks you a question. So the question being asked here, what is the new area, depends on this hypothesis. But by itself, it does not give you any new relationship. So what does this last sentence actually work? It works because now you are asked to get a result. That result depends on the new information in this sentence. That is, if the length and the width are both increased by 1 inch. So it's important to understand which part of the problem gives you the information to establish relationship, which consequently gives you equations. So we have to go back to the first sentence to search for more information. But as we just discussed, that sentence actually is information rich. All right, we want to use algebra to solve a problem, then we have to first set up our unknowns, right? It does not take too much time to see. It's a rectangle. We know a rectangle, there are two important parameters. That is the length. We generally want to represent with just say L, just for convenience, right? And the width, that is W. Once we know those two numbers, a rectangle is fully specified or is fixed. On the other hand, the two variables also are both involved in the first statement in two ways. One is area, one is the perimeters. Those quantities actually both depend on both L and W. We know that the area of a rectangle is just L times W, and in this case, it already told you that it's 108. So that gives us the first equation we need. And then the second part of the very first sentence or statement says that the perimeter of the rectangle is 42. And we know the formula for that. The perimeter of a rectangle is simply 2 times L plus W, right? You have four sides. You have 2 represented by L, 2 represented by width, length and the width. So the formula is just 2 times L plus W. And that is, the number is also given at 42. Okay. So in theory, that's all we need, because now we have two equations. They are not dependent on each other. They are area and the perimeter. They are not. By dependent, what we mean by dependent is that if you can somehow derive one of the equations, either directly or indirectly from the rest of the system of equations, then that equation is not independent. But in this case, there's no way, say, we get the first equation from the second or vice versa. So the two equations are indeed independent. So we have two equations, we have two variables. And by the general theory on system of equations, we should be able to solve L and W. And indeed, you can solve it. Just there's one small problem or consideration to take. And what is it? Did the problem ask us about the length or the width of the rectangle? No, that's not what we're trying to get here. So even if we can solve the equation, get L and W, that's not exactly what we need to do, right? So why don't you hold on for a second? Do not jump right into solving those two equations. This is super important for working on a math problem, especially a time constraint competition math problem, because you don't want to spend time on things unnecessary. If the problem directly asks you to solve L and W, you should do that, but you're not. You're not supposed to get that. What do you need to do? You need to figure out the area of a hypothetical new rectangle whose length and the width are just 1 inch longer. So that means that you got a new L, which is L plus 1, and the new W, which is W plus 1, and you want to get the area of this new rectangle. And what is that? We know, of course, the area is just length times the width. So it's L plus 1 times W plus 1. That's what you want. That is the quantity you need to solve. Of course, you can say, if I know L and W, I can compute this right away. You're absolutely correct. But is that the most productive way? Well, this is what you can learn if you never encounter a problem like this. Because we are not interested directly what L equals to or W equals to, instead we are interested in this. This is what we just preached earlier, right? This is the known information. What is the unknown? The unknown is neither L nor W. That's not what we are supposed to get. But instead, we are supposed to get this quantity. So you can argue from those two equations, you can get L and W first, then substitute those two numbers into this quantity. Yes, you can do that, but is that the best path or the shortest path? Well, we don't know yet. We need to investigate. So why don't we just take a closer look to see what this animal really is? It's L plus 1 times W plus 1. So we probably can expand it to see what happens. So by distributed property, you can easily write down L times W plus L plus W plus 1. Wait a second. This one looks much more closely related to the knowns directly rather than those two variables themselves, right? Once again, this is the unknown we want to solve. And those two in the green box on the knowns, what is the relationship between the unknown and the known? Well, you can argue there's an intermediate step, you get an L and W. Of course, you can solve that. But it looks that we have a much more direct relationship between the unknown and the knowns. And that is that we already have LW. Right there, it's just a number. That's right here. And we already have L plus W subject to a divisor of 2. But we also did that in the known. And the rest is just a number, easy number 1. So it looks like we can directly use the information in the already known quantities, which appears here and here, and substitute those numbers directly into the unknowns we want to solve. So clearly, we don't want to solve those two equations to get L and W. Instead, we will just directly use the information available. L times W, that's 108. L plus W, that can be very trivially done. It's 42 divided by 2, right? So this will give us 21. So this is just 21, L plus W, and finally you have 1. So that way, we completely shortcut the process of solving the two equations. Instead, we just directly use those equations to our advantage. And we get this 22 plus 108. This will be 130. Done. Okay, so the takeaway here is that really focus on what you need to do, not what you think you should do. Okay? Focus on what the problem asks you to do. Sometimes you can take a great shortcut, like in this one. All right? So, next problem. Okay. Well, this is more related to number theory, but still word problem regardless. So what do we need to do here? Well, Doug writes down his favorite number, which is a 2-digit positive integer. Okay. If you have done enough problem at this stage, you probably should think about how to represent this 2-digit integer. But hold on with that idea for a second. So why don't we read the problem completely? I'm just telling you that if you have practiced enough, so you want to develop some kind of reflective instinct about certain problems. In this case, you need to figure out how to represent a 2-digit positive integer. Let's finish reading the problem. He then turns the number into a 3-digit number by writing 7 at the end of his favorite number. If we can represent that 2-digit number, then we can do this, just adding a 7 or append a 7 at the end. So this new number is 385 more than Doc's favorite number. this sentence tells you a great relationship, right? If you can figure out a way to represent both the original number and the new number, what this statement tells you, there's a simple equation to write down because the new number is 385, more than the old number. So now you're asked to solve the original favorite number. So here's what everybody should know what to do. When you have a problem like this, there are certain fundamental basic building blocks you need to know. That is, how do we represent the two-digit number? Well, in general, we can write down the unit digits and the tens place digits, A and B, but because in algebra, if you write two digits back to back, usually it means A times B. Everybody should know that, right? In basic algebra, AB means A times B. So we want to avoid that notation because that's not what we mean. What we mean is concatenate, say, 3 and 5, put them together into a number 35, not 3 times 5. So in order to avoid that just notation ambiguity or confusion, we just add a head bar over just this is called bar. We use this notation to tell what we mean is the two digits combined into a new number. Okay, so now this is a really very basic skill everybody should be aware of. So we now figure out a way to represent this two-digit number. If now in the next sentence he turns this number into a three-digit number by writing the 7 at the end, so now we can similarly write down the new number as this one, right? That's what the statement tells you. So now the equation is just like the new number is 385. So this number AB7 bar equals to the original number plus 385. Okay? But you may get completely lost by asking yourself, what the heck is this? How can I possibly do this? I'm not sure what we are doing here. I learned something about the algebra and variable, but this does not seem to be anything like that with this just weird scene, overhead bar right there. But this is why we emphasize that you need to learn this basic skill. That is, when you have a notation like this, it can be transformed into the typical algebra that you do know how to work with, because this is just represent a number. So this is readily equals to 10 times A plus B. Why is that? Because that's just the definition. B is the unit digit. A is the tens place digit. That means really you can break it down into something like AB equals to A0 plus B, right? Agree? So, and A0, you can readily convert it into 10 times A because A is just a digit. So clearly, this relationship holds up, and this is a very important basic skill when you work with a problem like of this nature. You represent a number in this very kind of weird way, but then translate it into the typical algebra that you are familiar with. This is nothing but 10 times A, the tens place value, times 10 plus the unit digit B. And similarly for this one, this would be, because now A becomes the 100th place digit, this will be 100A plus 10 times B plus 7, right? So now you can translate this equation into something you are actually really familiar with, because now on the left-hand side, it's just 100A plus 10B plus 7. On the right-hand side, it's 10A plus B plus 385. Okay? So this is the significant progress that we just made, because now we know At least we know how to manipulate this equation, and it doesn't take long. You can see that we subtract something, we get a b, and convert this into 9b, cancel the b on the right hand side. We also cancel 10a on the left hand side to make this 90, and we subtract 7 from the right hand side, so this becomes 378, I believe. So from that equation to this equation, you can write something like this down. All right. Well, in general, you have two variables, but you only have one equation. You cannot solve the equation uniquely. But this is a special case. Why? Because a and b represent two digits and numbers, so there are a lot of constraints on them. And this is generally called Diophantine equation. For now, you don't have to worry about that. What that means, just think about AB represents a number, so there are certain constraints, and clearly it's not too difficult to understand. B in theory can be anything between 9 and 10, any of those 9 digits, right? And A, on the other hand, A cannot be 0. A can only be 1 to 9, any of those. So A and B cannot be arbitrary numbers. They have to be subject to those constraints. So we can further do something, because we can factor out 9 here. So it's 10a plus b equals to 708. Hey, wait a second. Now this guy looks familiar. 10a plus b, that's exactly the original number. Remember, 10a plus b. And wait a second, what was the problem asking us to do? What is the favorite number? That was the number that we need to solve. It's just 10a plus b. We're not interested in what exact digits a or b is. We are interested in what 10a plus b is. Also, once you know that, you can figure out that anyway. But more directly, we are asked to figure out this number exactly. So, it's a surprise. It's a sweet surprise. So 10a plus b is simply, this is divided by 9, that's 42. What a nice surprise, right? So what we learn from this is a couple of tricks. It's especially important understanding a standard trick like this is that when you work with some digit representation of a certain number, you can generally start with a kind of weird representation, but being able to translate this representation into a typical algebraic representation like this. So AB7 bar is simply 100A plus 10B plus 7. This is very important. So this problem, of course, the very reason we could have such a sweet surprise was because the problem had been so written, the problem writers expect you to get this. All right? So that's the this problem. So because this is the first lecture, we are a little bit short on time, but we will continue. So if you have to go exactly at 5 o'clock Pacific or 8 o'clock Eastern, feel free to come back later to finish watch the remaining of the video. Because we are using YouTube Live, all the videos should be shortly available right after the live streaming is over, typically 10 minutes later. So if you have time, continue to watch to the end while we are live, or you can always come back to finish the couple of remaining problems. So just a choice. So I believe we still have 2 more problems to go, so it may take 10 minutes extra because today is the first day. We did spend a lot of time to talk about the general administrative things, not just mathematics. So so bear with me. So next problem. Okay, problem number A from mini number 14. find the least positive integer that leaves the remainder when you divide it by 2, remainder of 2 when divided by 3, remainder of 3 divided by 4. Jeez, this is just continuing without end. Remainder of 4 when divided by 5, remainder of 5 when divided by 6. What is this guy doing? And the remainder of 6 when divided by 7. Do we really need this much repetition? It sounds a very complicated problem, isn't it? Yes and no. If you are a very careful reader of the information, you will recognize one particular thing which is not just interesting but also very helpful. And that is that we're trying to solve some number theory problem. We are doing a division with remainder problem, but we got a lot of conditions, actually 1, 2, 3, 4, 6 different conditions, but they share one very obvious and very important trait. That is that whenever you divide the number 2, 3, 4, 5, 6, and all the way to 7, 6 cases, your remainder is always one less than that divisor, right? It's not too difficult to see in this problem because you got 1 when remainder 1 when divided by 2, you got remainder 2 divided by 3, and so on. So clearly, each time you are just one short of dividing that number perfectly. What does that suggest to you? If you have never worked on a problem like this is a good opportunity to learn. But for those of you who actually did any problem like this, it's so impressive. I guess 80% of the time you won't forget about it. If you did forget it, do a similar problem second time. That will give you another 80% of chance of not forgetting it. So twice trying at it, the overall probability would be only 4%. You should have 96% probability of not forgetting it. If you still unfortunately hit by that 4%, try it one more time. So next time you have 0.8% of chance of forgetting it. Well, 3 in a row, that's quite remarkable. So what is that trick? Before we discuss that, this is important, okay? The great mathematician and the great math educator George Polya has a great tip for you. When you work on a difficult problem, try to think about a similar or perhaps easier, simpler problem that it did work before and remember how to solve it and try to make a connection. Usually the more difficult problem is just straightforward extension or maybe adding a little bit just kind of manipulation or a little twist here and there to make it work. That's just solely based on your past experience. That's very important because like the great saying says that don't reinvent the wheel, right? If you have already worked something out, if you can based on that just do a little bit of extra work, solve a new problem, how wonderful that is. So this trick is quite standard because you think about it, every time you are just one short of dividing that number perfectly, what can you do? You just add 1 to that x, which represents the number you don't know. Because if we know x plus 1, of course, we subtract this new number by 1, we get back to x. So we don't have to solve x right away. Instead, we can solve x plus 1. And in this case, what were we supposed to do? Find the least positive integer, meaning the smallest, that can meet all those 6 conditions. But if x is the least, then x plus 1 is also the least for x plus 1, right? So, but x plus 1 gives us the nice property that it can be perfectly divided by 2, 3, 4, 5, 6, and 7. I believe 7 is the last one, right? Correct. So that means that all those numbers are divisors of x plus 1 if x is the least such number. In other words, now the problem has been translated that find the smallest number. In this case, it's represented by x plus 1. That can be perfectly divided by all rows. And that we know what it is. What is that? That's just the least common multiple, the LCM of all of them. Maybe you only learn LCM representing the least common multiple of two numbers, A and B, but that can be straightforwardly to extend to more numbers, because once you know the LCM of 2, then you just add one more. So you should know this general strategy, right? If you have three numbers, what is the LCM? The least common multiple of the three of them. You can first get the LCM of A and B. Then get another layer of LCM. You first figure out the LCM between A and B, and then take the LCM of this LCM and C. It's not too difficult to actually prove this is exactly what you need to get. But regardless, if you know this fact, great. If you don't know, it's not too difficult to figure out the logic here. So clearly 2 and 3 already it's part of 6, so we can actually cross out 2 and 3 right away because that is 6. So what is the common multiple of all of this? 4 and 6 share a common factor 2, and that's the only one among rows. So really, 4 and 6, the multiple LCM is just 12. And 12 and 5, 7, they are all pairwise mutually prime to each other. So really, you have to multiply all of them together, because 5 plus 7 are prime numbers. You cannot do anything with them. You cannot save you any common factors, because 12, it has 2 and 3. It's 2 squared times 3. 2 and 3, they are primes. And 5, 7, they're also prime. You cannot do any better. So the LCM among 2, 3, 4, 5, 6, 7, it's really this number. And we know this is the smallest number that can be perfectly divided by rows. Then we already know what we were looking for. It's just this perfect LCM subtracted by 1. Because once you subtract by 1, then every time you use any of those divisor to divide this number, the new number minus 1, you are 1 short. So the remainder will be just 1 smaller than the divisor. And that's the constraint we initially face. Therefore, the answer to this question is just 12 times 5 times 7 subtracting 1. All right? If you don't believe in me, try to see whether this gives you all the remainders like the problem gave you. Okay. So the takeaway from this problem is that this is a special problem where it has been set up. There's a very easy shortcut readily available, and you do need to take advantage of that. Well, if you read the solution, the official solution later, of course, this shortcut is there, but there's also a more complicated, long and winding path to get the correct answer. You can do that, but it's very unproductive. And certainly, if you do that during the math competition, I'm sorry, you waste a lot of your time. Okay, the last problem, this problem perhaps is the most challenging problem of the day, so we leave it at the very end. And this, once again, a number theory problem. But this problem is actually very similar to the video problem. So if you have actually studied the video, and then you should know how to do a problem like this. Before we do it, I want to make a 1-minute comment of this. For a problem like this, you have more advanced tools. In this case, like a modular arithmetics or linear congruence, those powerful tools for you to solve problems like this. But in general, in AMC8 and Mathcounts, you are not supposed to know those advanced technique. So you are kind of using very rudimentary method to solve this problem, which actually mimic the underlying principle of those more advanced tools. So essentially, you are using those concepts or the underlying concept of those advanced tools just without knowing that effectively you are using those tools in a more complicated way. Let's put it that way. But that's actually what math competition should be. Because if everyone say, for a problem like this, I know how to use a more advanced trick that should be only high schoolers know, or even college students know to solve this problem, that's very bad. That's unfair. If you do that, everybody is forced to go into arm race, right? As a middle schooler, you need to learn high school materials, even college materials, in order to solve a problem faster than your competitors. That's really, really bad. Okay, so let's just try to solve with this problem with some more just a kind of basic approach. So in this case, once again, you need to find the least positive integer, meaning the smallest, that need to meet 3 separate conditions. And this time we are not as lucky as we have last time, where you have a common factor can easily shortcut all the 3. Last time 6 conditions, but this time when you dividing this number by 5, you got a remainder 3. Dividing by 9, remainder 7. So why don't we make a list and a table, right? So let's just say this is the divisor and this is the remainder. When the divisor is 5, you get a remainder 3. When divisor is 9, you get a remainder of 7. And when you divide this number by 13, you get a remainder at 9. So, by the way, this is also kind of a routine trick or skill you need. This quickly translates the information from English to some mathematical notation. In this case, it's a table, but still much easier to understand. It's not a true mathematical notation per se, but it gives you very simple and very direct visual summarization of the information. So now, what is the smallest of such number that can meet those 3 constraints? So if you have more powerful tools like linear congruency, you can use a modular arithmetic and solve those equations, linear congruency equations, but you're not supposed to do that. So we're trying to figure out how we can solve this problem just from this table, right? Here's where Georgipolia's suggestion actually can help you. When you face a more challenging problem, think about a problem that you already know how to solve. It's not the exact same problem. Perhaps it's just half of the problem, but perhaps it's 70% of the problem. Regardless, it's related and usually it's simpler. Do we have such a problem? Actually, we do. We just did 5 minutes ago. And that is, in the last problem, we have 7 divisors. And the remainders all share properties that they somehow have the exact same property, that is 1 short to make the division perfect. Every time we just need 1 more to get a perfect division. And that's a great property that we took advantage of last time. But how about this time around? Well, this time, this guy's too short of a perfect division. This guy, yeah, he gets 2. But the last one, we need 4. So if this one is also 2, then it's very easy, right? It's just essentially the same as the last one. But unfortunately, it's not the case. This guy needs 4 to get a perfect division, the 13 guy. Regardless, we still recognize that if we take advantage of this, we can do that. Hold on a second. I think I may write something. Yeah, this is 7. I'm sorry. This is 7. So this is not 4. This is 6, but it's the same thing. So this is one way to think about how to solve this problem. Okay? it's logically equivalent to the other, or at least in terms of the complexity, to the other solution. That is that this is one possible way we can solve this problem, meaning that when you divide this number by 5 and 9, every time you are 2 short of having the perfect division. So you can try to, with our last approach, say, I don't want to solve x directly. I want to solve x plus 2. If that's the case, you know in the first two divides of 5 and 9, you get perfect division because you're adding 2 to x. So when you divide this number by 13, instead of a remainder 7, you should get a problem 9. So this actually reduced the problem from a 2-divisor problem, a 3-divisor problem into a 2-divisor problem. Okay, because 5 and 9 now can be combined into one divisor, that is 45, because 5 and 9 are mutually prime. They don't share any common factor at all. This is the one way of doing it. Of course, the video has another way. Another look at this problem is that instead of, from this perspective, say, how many more you need to make perfect division, you can take those last two. It's essentially similar idea, but in this case, you already directly get, say, if you divide this number by 9 and 13, every time you get 7, the same remainder. That also achieved exactly the same effect as the first observation. So first one is just that if you add this number 2, you get a perfect division. What this tells you is that essentially you subtract, instead of x plus 2, if you x minus 7, you get a perfect division as well, right? So the two logically actually very similar. Take either approach, it's fine. So we will take, in this case, because we just did with last problem, but see what we could do with, say, x plus 1 in the last problem. So now we know if we work on x plus 2, we can take advantage of the first observation that in both cases you just need 2 to make a perfect division. This time around, we just try to test our capability. Say we stay with the second observation, that is that the remainder is the same when you divide this number by 9 and 13. What this means is that, of course, you can work on x minus 7, but it doesn't really matter. All it does is that because 9 and 13, they are mutually prime, they don't have any common factor at all. So essentially, this is equivalent to, if you divide this number by 9 times 13, this is the new divisor, you still get a remainder of 7, obviously. And this is actually equivalent to the first one, because if you have this property, you certainly will have this group of 2 properties, and vice versa. Essentially, what this means that this is equivalent to this. Okay? So this condition is actually exactly the same thing as this group of 2 conditions. You can replace it with that. So with this, without the more advanced tool like modular arithmetic, we significantly cut down our problem from a 3-divisor problem to a 2-divisor problem. Now we can use some ad hoc or brute force approach to solve this problem, because we know this problem will be something like multiple k times 9 times 13 plus 7, right? It must be in this form because it always has a remainder 7 when divided by 9 times 13. So this number must be in this form generally. And you just need to test when it can actually meet the missing condition that we circled here. When will this number get a remainder 3 when divided by 5? So without modular arithmetic, we can always try that. So what is 9 times 13? That is 117, right? Once again, you need good number sense. You need to be able to do this mentally. How do we do this? There's all kinds of just mental math tricks. 9 times 13, that's 10. You distribute it properly. That's 10 times 13, which is 130, subtracting 13, that's 117. So essentially, your representation of this number based on those two conditions is 117 times a k plus the 7. So you can verify when this guy divided by 5 will give you remainder 3. The first time you meet this condition, you will be done. Okay? So let's try k. Well, in theory, it could be 0, right? So that means that this number is 7. But clearly 7 divided by 5 give you 2. That doesn't work. So how about case 1? Well, the good thing with dividing by 5 is that we only actually look at the unit digit. That's more than enough. Because 5 is just a factor of 10. So any number divided by 5, the remainder will be determined by the unit digit. That's a wonderful thing. So if case 1, the unit digit is actually 7 plus 7, that's 14. So the remainder is actually 4. It won't work. What if case 2? Well, 2 times 7, that's 14. The unit digit now it's 4. 4 plus 7, that's 11. So the unit digit is actually 1. That won't work. So what if case 3? 3 in this case, 3 times 7, that's 21. Unit digit is 1. 1 plus 7, that's 8. 8 divided by 5 is 3. So when case 3, we will get a remainder 3. And this is the very first time we can get this. And that must be the solution where we need to find the least such integer. So the answer is 117 times 3 plus 7. Okay, so this is the smallest integer that can meet all the 3 constraints. Okay, you can see that in this approach, we just based on this fact and then try to take a brute force way to meet the first condition. As we mentioned, if you use similar concept, we can also based on the first 2 set, and that is that would be something like a 45, because 5 and 9 is 45k, then minus 2, right? Because this guy will be 2 short of perfectly divided by 5 and 9, and you test when this can gives you a remainder 7 divided by 13. But this is one more trick for you. You recognize which one is better when you perform the last step. Obviously 5 is easier. You want to divide a number by 5, not divide a number by 13. So that's one of the reasons we chose starting with this last one instead of using the first one, because there are some just kind of tricks. Well, initially you did not recognize, but very soon it will become obvious to you. Being keenly able to detect such things early, it's a skill that can only be developed over a long time. Okay, because in our approach, we only try to perform the last step with a divisor of 5. Imagine if you have to do that with a divisor of 13. That could be truly, truly painful. All right, that's all we have. I'm sorry for extending the amount of time, but I hope you have learned something. We will continue next week. Thank you very much. I will see you next time. Bye.